Hello and welcome to the next installment of our Saratech Enablement series. My name is Monique Anderson. I'm the Marketing Coordinator at Saratech and I'll be your host today. Presenting today we have Mark Anderson, who is an Application Engineer here at Saratech, and he'll be teaching some tips and tricks about NX-CAM. But first I want to tell you a little bit about the Saratech Enablement series that we've had great success with. We usually run about 30 to 45 minutes and our training is always led by subject matter experts. We cover topics including FEMAP, NX, Solid Edge, Team Center, and much more. So be sure to check out our website for dates and times which may vary in the coming months due to customer feedback. Our goal for this Saratech Enablement series is to help you get the most out of your software, to share knowledge amongst each other, and to build a community of users that will help empower each other. As always, this is an open forum and we look forward to you participating in the training. If you have questions or comments during the presentation, please type them in the chat box to the right of your screen and I'll kindly interrupt Mark and let him know your comments and questions. And with that, I'll pass the baton to Mark. Thank you.
Hello, as Monique said, my name is Mark Anderson. I'm an application engineer with Saratech. And today we're going to go over simulation versus visualization and the limitations of visualization and the vast improvements that they made in simulation. So here's our agenda for today. We're going to go through visualization and material removal, limitations with visualization, the integrated simulation and verification, which is called ISNV, the toolpath simulation, which is the internal NX code. That is the CLFS file from NX that's driving the simulation. And then we'll go through toolpath simulation, the G-code simulation, I'm sorry, that's external NC code driven from the post processor. And then I'll show you a brief explanation on what the machine control emulation is, or VNCK, virtual numeric controller kernel. And then we'll also go through running a G-code simulation from a G-code file, an MCF file, and which is called reverse simulation. That will be exactly the same as something like VNCK. And then we'll talk about passive post-processing versus simulation enhanced post-processing. So in this slide, we're going to talk about the third-party simulation softwares. As I said, VNCK and other softwares. It has additional costs. You have data translation and transfers. You have duplication of models and tooling, and you're constantly switching between systems. And what's not mentioned on this slide is that when you use a third-party verification software, it creates an additional file. So what you're going to have is you're going to have three files. You're going to have your NX file, you're going to have your MCF file, then you're going to have a verification file, and then if you use an optimized software, you'll have a fourth file that you have. And what that does, it creates an organizational nightmare. So we have our NX-CAM, and then we have NC programming, which creates our toolpath data. Then we have post-processing, which creates our GPUT output file. Then we have our external simulation, and then the machine tool simulation, which is your G-code driven simulation. The integrated G-code simulation, the ISNV, what that does is it uses NX-CAM and it uses the post-processor output and then programming and simulation in one system, and it's all done in an NX. And what we have here in this tier is NX-CAM, then we have our NC programming toolpath data, post-processing, and then that post-processed data is then used in this integrated simulation and it drives the machine tool simulation. So it's exactly what's going to be done on the machine tool itself. Now in machine control emulation, the VNCK, it has the first three tiers of the integrated simulation, but it has a fourth tier on the bottom there. It's driven through the cinemeric VNC control. So you take your G-code and then it drives it through the cinemeric control that's actually on your machine. So it validates cycle calls, variables, and different things that's indicative of the machine control itself. So this fourth tier, if you have a cinemeric control, is the complete simulation solution that Siemens can offer you. At this moment, we don't have any simulation, any VNCK kits for FANUC or Heidenhain. It's just cinemeric control, but they are in talks of making those available to us. Now the reverse G-code simulation, many people, they don't understand or realize what power they have in the package that they've bought. The G-code simulation, it's included in your total machining packages and some of the lesser packages as well. The reverse G-code simulation, it can be used to verify legacy programs that were created before the use of NX. It saves costly setup time. It shows your crash moves, lists gouges, and shows the undesirable machine motion, and it's all in the same simulation user interface. So let's go into the demonstration. And with this, you can see I have this mold up here. And I pulled up a 5-axis toolpath that's going to be cutting these letters down at the bottom of the mold cavity. Well, with the just standard visualization in our Verify, we do have our 3D dynamic tool display, which will show our material removal. But since I'm not going to cut the material beforehand, I don't want to play that because it would clog up the view. So using the replay, you can see that this tool is already tilted off of center. When we go through this toolpath, I'm going to step it through. You can see that the tool is doing all the driving motion, which is not indicative of what's going to happen on the machine tool. So all of these motions where you see the tool doing the tilting, that is not a representation of what's going to happen on the machine tool itself. So how are you to know that that's going to not crash on the sidewall or it's going to cut as you want it to? So what we do is, and I want to show you another rest milling operation just to show you the full 3D dynamic. And this, for 3-axis milling, 2-axis turning, this may be sufficient. But anytime you get into 4th axis, when you have another driving axis or live tooling or mill turn with simultaneous front and rear turret or upper and lower turret, the simulation, the G-code driven simulation almost becomes a must. And when you are doing multi-axis machines, simulations with synchronization, you have to have the G-code driven simulation because that's the only way to get to the synchronization manager. So you can see that the material removal and verification, it will suffice for most of your applications until you get to 4 and 5-axis or multi-axis work. So now let's go and turn the machine tool on. This is a DMU50 Mori kit. Let's turn the door off. So I'm going to go in here and I'm going to grab that same operation. And I'm going to show you the difference in toolpath simulation and G-code simulation. So when we go in here to simulation, you can see that I have machine code and toolpath. Toolpath is internal NX code driven simulation. And you'll see this when I tell this to go, the spindle is just going to automatically appear with the tool in it and it's going to start cutting. Like that. So as this cuts, it does show you all of the machine motion. It will show you the rotation axis and it will give you a full definition of what's going to happen in the machine tool. The only difference is it's not running off of code. It's not running off of G code itself. Let's go down here to that 5-axis operation. This is just another 5-axis operation. So now once I'm doing this, you'll see the full representation of the machine tool. And as I said, this is still toolpath simulation. See, we have a collision there. We didn't see that on verification. We didn't have any gouges listed. We didn't have any collisions. We didn't have anything listed on the verification because it didn't know what was going to happen with the rotational axis. But now you can see all of our axis in motion. We have a complete visualization and verification of the part and the machine tool itself. And anytime that you are doing a visualization, any of the driven axis, the table, any of the machine tool will be automatically set as a check surface so it knows that it can't collide with those surfaces. You can manually shut them off, but you would never want to do that. So you can see, now that there is toolpath simulation. So let's go ahead and show you G-code driven simulation. So what this is going to do, you can see this has the yellow mark on it, which means it's not been post-processed. I'm going to switch this to machine code simulate. Now what this is doing is it's running in the background. It ran the post-processor. So it's physically running the G-code that would run in the post-processor if I posted the code. And you can see the G-code simulation. What it's going to do is it's going to show actual full machine motion and kinematics. So right now it doesn't know what tool is going to be in there. So it's going to physically do a tool change. Now that's exactly what the machine itself would do because it saw an M6 tool call. And you see the visualizations are very close, but I guarantee that they're not going to be the same. If you took the CLSF file and looked at that or driven it through a different post processor, it wouldn't be the same as this machine code simulation. But you understand the point of what I'm trying to get at. You want to see these machine motions and the driven axis in motion so that you can verify everything on the machine tool. And verification would not ever be able to handle this. So with that, let me move on to the reverse G-code simulation. So you see I have operations here, but they're all out of date. And then when I go into my program view, I have no operations here. I put them all into the unused items. So they're not being registered as all. They're not being identified. They're not being tracked. Nothing's happening with those. They're blank operations. So what we would do is go into menu, go under tools, and at the very bottom, it says simulate machine code file. We'll choose that. This dialog will come up. You'll reach out, find this MF. It doesn't matter what the extension is because you label that in your post-process dialog. This is called MPF, but it doesn't matter. Machine post file, there's MCF, machine code file. It's just whatever you and yourself want to name it. We tell it that that's the code file we want. It loads it up in the register. Now, the only thing that we would have to do is we would have to do the same thing as Vericut. We would have to have the simulation kit for the machine tool. We would have to have the output file, and then we would have to build the tools exactly as they were in the machine code file. We'd have to have the part set up to where the machine code file says it should be. And the way that you do that is right here we have our machine code file. And then here we have our setup sheets that tell us the information that we need. So if we had a old file that all we had was setup sheets and a machine code file, we could turn that around, build the simulation, input the machine code file, and we could run this to verify. And it will still list all the gouges, it will list crashes, it will show you with red if there is a crash on the machine tool. And if we build the simulation correctly, it will do exactly as it would on the machine tool. This can be very handy for shops that have old legacy programs or that has just switched to NX so that they can drive their simulations and they can see what's going to happen. This will save valuable time on the setup due to operator confidence. When you have an MCS file and you have setup sheets, you have really no information on what's going to happen on the machine. So that in turn makes the setup person have to sit there with their hands on start stop or emergency stop to make sure nothing happens. So that's a very slow process. When we can validate this program beforehand, it gives the operator a lot more confidence in what they're about to do, so that they can set it up and they can know that, okay, if the tools are touched off correctly, I've already seen what the operation is going to do. I know it's not going to crash. I can let it run through. So it will gain you valuable time in your setup process being able to run through this reverse G-code. Now, the reverse G-code is only available in the G-code simulation. So I'll explain the different parts. When you, just out of the box with some of your total machining packages, you do have the G-code simulation, but most of the packages only have toolpath simulation, which will give the toolpath from the NX file, but it's not the G-code driving the simulation. And that will suffice on most of your simulations. But if you want an absolutely accurate simulation, then you must have the G-code simulation, which is an add-on to the standard toolpath simulate. And then the reverse G-code comes with that G-code simulation. The machine controller emulation, or the VNCK kit, that is also an add-on that goes to the G-code simulation. So that's the 4 levels of simulation. So now I want to show you the most complex simulation that you must have the G-code simulation for. And as I said before with the synchronization manager, this has an upper B-axis and a lower turret. Any time that these are going to simultaneously work on the same part, traditionally you have 2 programs. You have an upper turret program and a lower turret program. Those 2 programs are tied together with wait codes. So that's tool 1 on the upper turret runs the same time as tool 1 on the lower turret, and they have a wait code that tells them to go together and then separate. So you have to have that sync manager to be able to align the tools the way that you want them and to make them run the way you want them. If you don't have the simulation, then you're never going to pull up the simulation, the sync manager. And you see I'm in geometry, so I need to get into program order view. Now when I hit simulate, it says I'm trying to simulate a synchronized toolpath. So it's going to bring open the synchronization manager. As it's loading the file, it's running through the post processor. It'll load the file, it will read the file, it'll read the weight codes, and then it'll let you run the program in simulation. But if you didn't have this G-code simulation, then how are you to synchronize your tools together? You can do it manually, but that's just taking apart the complexity of NX. So you see here we have our channel 1, which is upper turret, channel 2, lower turret, and then we have M10, M10. That's our weight codes to tell it when to go and when to stop. So if you can see that if you did not have synchronization, it would be very difficult to understand exactly what this program was going to do. And from experience, on the floor experience, I have 20 years in programming of different style CAM systems. I've been with NX for about 5 years now. And every one of your CAM systems, they're going to produce the CLSFS file, and then it's going to run through a post processor. So your code is only as good as your post processor and your machine toolkit. What NX has done is they've given probably 16, I believe it is, simulation kits that you can alter if you choose to. And they're out of the box so that you can see exactly what's going to happen. You can practice with them, you can test them out. And then if you get very specific machine tools like that DMU that I just had, you can purchase them from Siemens and it'll be a certified DMU product, which we will plug that into NX and it will run right from the beginning. And if it'll be to your serial number of your machine so that you can guarantee that it will run right out of the box. So I'm gonna let this run for a little bit longer because I want you to see the pickoff. Now the pickoff is one of the hardest things to program inside of a CAM system on a mill turn, because that distance between sub-spindle to main spindle is an unknown. So you either have to have known queued points on that, or say face to face of spindle is X distance, subtracting the part gives you the distance that you need to go, including your jaws. Then you sometimes have to time the jaws to get around features of the part. So here's the pickoff, cut it off, brought it over, did some face milling, turning, doing some drilling, and then it's going to finish up with helical milling. So that was the most intense simulation that you're probably going to run into in NX, a dual channel machine. And it handled it very simply, very simple. So now, getting back to our presentation. In summary, 2- and 3-axis milling, or 2-axis lathe, it doesn't necessarily need full G-code simulation, but you are going to be well ahead by having it. If you do have it in your current platform, then I implore you to use it, to test it out. I would like to do one thing before we go on. I'm going to show you exactly where these simulation kits are. If you go into your hard drive, into the standard install of NX, sorry about that, Siemens, NX11, in the mock folder, your mock folder contains all of your machining information. So if you go into samples, you see you have NC simulation samples and then try NX CAM. In this simulation sample, we have Sim 1 through Sim 16, and that's what I just showed you with Sim 15. But there is a head change mill 16. So right here is where you go to get those simulation kits and to test them out. Back to our 4- and 5-axis multi-purpose machine tools. They will definitely need the simulation, whether it's toolpath simulate or machine G-code simulation. They'll both suffice, but you're going to be further ahead having the G-code simulation. It'll eliminate the passively post-processing. And passive post-processing, just as an explanation, passive post-processing is when you post-process a part using a verification or a visualization style software. So you post-process G-code not knowing what the machine file is going to do, not knowing what the machine itself is going to do. So then if you go out on your machine or your verification software and you see an issue, now you have to go back to your CAM system, alter, go back to your simulation software, verify, and back and forth and back and forth. So using a G-code simulation tool at ISV, you have the machine tool in the background. So if there's any need for the tool to adjust to get the axis position that it needs from the machine tool, it'll do it inside of NX and not through the simulation software. So it's called simulation enhanced post-processing. So it eliminates the passive post-processing and the need for the third-party simulation software. Legacy programs can be ran through the reverse G-code simulation to gain confidence and setup time, like I said. And the NX reverse code simulation gives the programmer confidence, which speeds up the setup process. So if anybody has any questions about the simulation, I'd be more than happy to answer them. What's new in the next session is what's new in FEMAP 11.4. It starts Wednesday, August 2nd, 2017 at 11 to 11:30 Pacific time. And then we're ready to take it to the next level. We offer hands-on training, classes for software of all user levels, engineering services that are addressed to your demand for advanced engineering capabilities. We do all type of service work, post-processing, contract programming, pretty much anything that has to do with NX or Solid Edge we do. So with that, I thank you. And I'll turn it back over to Monique.
Awesome. Thank you, Mark, for a great presentation today. And to our attendees, we will be posting this video to YouTube later today. Please feel free to pass it along to your friends and colleagues, and be sure to subscribe to our channel. Follow us on Twitter and LinkedIn for upcoming enablement session dates and topics. And if you could please just stick around for 30 seconds after to fill out our survey. Let us know how we did and what you liked. We really appreciate your feedback. Thank you again so much, everyone, for attending, and have a great rest of your day.
Thank you.